Thank you for the introduction. Thank you for having me here. I was sitting here preparing to be short, but the last lecture was fast, so I've got time. And it will be completely opposite what we've heard from the last talk. One of the messages was that the nice, shiny statistical images are not important. I'm working with MRI. I can't stand not to show you beautiful red and blue 3D images. Well, that's what my science is. The title in the program booklet was something about brain and health and disease and structure and function. To be honest, it was in the middle of the night when I got the email, and I figured out something very broad. I can speak whatever I want to. Yesterday night, however, I figured it would be just a bit too broad, so it's going to be about headache. In my lab, there are researches running on about headache disorders, multiple sclerosis, and Alzheimer's disease. So it's just 1/3 of that research, what we are doing. So first of all, I'm a neurologist, and let me tell you something about what headache is. If you think about headache, there are different kinds of headaches, basically two categories. The first is secondary headache. Secondary, which has a cause, anything. A tumor growing in a brain, someone had a stroke might cause headache, or if you just hit your head, that's a secondary headache. Probably you're going to have an exam tomorrow. That's a secondary headache. No, but we've got more interesting stuff, which is primary headache disorder. That's migraine. One of the most important and probably the most interesting one, which is a very common one. It is affecting roughly 10% of the population. Women are much more affected than men. It's usually the disease of fairly young people. It's not life-threatening, but quite troublesome if someone has a headache attack for several hours or even several days, let's say 5 times per month, which is not really uncommon for these patients. And it's really severe headache. It's coming usually unilaterally, it's throbbing. It is coming usually with vomiting and nausea, with photophobia. And sometimes this kind of headache is preceded by a so-called aura, in which part of the headache, there is no headache yet, but patients are experiencing some kind of, for example, visual symptoms like flickering lights, zigzag lines, or stuff like that. It's preceding by half an hour the headache period, and these migraineurs are called migraine with aura. And we've got patients not having aura syndromes, just migraine headache. And the other kind of headache, primary headache disorder, what I'm going to talk about today is cluster headache. It's a rare disorder. It's very rare. Probably in Szeged, we found in a recent couple of years 20 of those patients. It's a very severe headache. The pathomechanism shares some commonality with migraine, but we don't really know how's it working or how does it develop. It's a very severe. Patients are telling you that's probably the most severe pain what you ever can experience, and it's strictly unilateral. A very interesting thing, the painful episodes are coming in bouts. Bouts meaning that I've got a patient who's got headache usually before Christmas for a couple of weeks, and headache is presenting usually in the middle of the night, usually around midnight, and it's like the clock. So that's why we think hypothalamus, which is an internal clock, is playing an important role. So that's about headache, and we are investigating headache with MR, magnetic resonance imaging. So hands up, who ever seen an MRI in the room? Okay, a few of you. That's good. MRI basically is a huge magnet. The thing what you can see here is the brand new one, what we just implemented 2 days ago here in Szeged. It's a 3 Tesla GE scanner. 3 Tesla. You might remember this from movies. This is an electromagnet which is picking up car wreckages, right? That's about 1 Tesla. So the scanner in the basement, we've got a 3 times more powerful. It's a very powerful magnet. So whenever you see a magnet, be sure that you do not go any close before you are checked completely for any kind of magnetic thing. For example, your bank credit card will be destroyed for sure. So in the clinical routine, we are making nice images. And that's something what we are using very frequently, but it's a research tool also. Let me tell you a little bit about how does it work. Well, it's quantum mechanics, and I'm a medical doctor, so I can't. But I'll try to fake it. Basically, you've got a load of protons in your brain, well, in your body, but one water will contribute to 2 hydrogen. Hydrogen nucleus is proton. And protons are small magnets. That's the easiest way to think about it. And if they are a small magnet and you've got a huge magnet, you put a lot of proton into that huge magnet, well, they will align with the main magnetic field. Well, the time it takes them to align with the main magnetic field is called the T1 time. It's one interesting property of the certain tissues. And depending on in which kind of molecules and which kind of tissue the proton is, you're going to have different kind of T1 time. And based on that, you can separate gray matter and white matter and CSF, cerebrospinal fluid, or stuff like that. And the other thing is what you can do is you can flip, if those are aligned with the main magnetic field, you can flip them to 90 degrees and they start to rotate. The speed of this precession, this rotating movement, is only dependent on the main magnetic field. Meaning, if something is disturbing the magnetic field, that this coherent precession will destroy, and you're going to see a decaying signal. Well, and that's what we are measuring, how fast the signal is decaying. And I will come back to this later on. Today I'm going to talk about 2 major uses of MRI in research. One of those is diffusion MRI, and the other one is a functional MRI. Diffusion MRI is working in a way that we are measuring the diffusion of the protons, mainly in the extracellular space. Well, extracellular space, but you might remember that in the brain you've got neurons which has axons. And axons are aligned in fiber pathways. So a lot of axons are running perpendicular, parallel to each other. And those axons has a myelin sheet, a lot of a lipid membrane. And water can't cross lipid membranes easily. So if you measure the diffusion in a very short period of time, you can show that along the axons, the diffusion is faster than perpendicular to the axons. And that's how we are measuring microstructure properties of the brain. So more packed the axons are, more myelin you have, less diffusion perpendicular to the axons, and more diffusion parallel with the axons. You've got a lot of different kind of measure. Basically, you can measure the diffusion from 60 different directions. That's what we are doing. And if you measure it, you get a probability map of my colleague are calling this a potatoid. A potatoid basically is a lot of measurement, and if you run a singular value decomposition on that, you can get the 3 main axes, the long axis and the 2 perpendicular axes, and that's giving you a direction of diffusion and a magnitude of diffusion in the 3 main directions. And from that, you can calculate a lot of different kind of parameters. For example, fraction anisotropy. Well, that the projector is not really working fine. If you measure the fraction anisotropy, that's a value between 0 and 1, it's close to 0 if it is very elongated a diffusion pattern, for example, in the white matter. But if there is no membrane, well, the diffusion profile is more spherical, for example, a cerebrospinal fluid in water, and the fractional anisotropy is close to 0. And that's what we are usually investigating. And now coming back to headache disorder, this is about migraine. This is a study by my colleague, Nicoletta Szabo. One of the first studies we published from here, from Szeged. We compared migraine patients with controls, with healthy controls, age-matched controls. And what we've seen that there is a spot in the frontal white matter over there, the little reddish dot, which has a different microstructure in migraineurs than in healthy controls. You might ask that, why is it any interesting having a frontal white matter region in migraineurs which are having an altered microstructure? I'm telling you, if you do a tractography, so you are looking at fibers running from that particular part of the brain, and you are looking at where are they going, it's getting very interesting. Some of the fibers are running to the cingulate cortex, which is responsible for the emotional aspects of pain. Well, some of them are running to the thalamus. Thalamus is the first relay nucleus in the brain of the sensory pathway. And then some of those are going to the insula, which is responsible for all vegetative, parasympathetic and sympathetic changes related to pain. And some of them are going down to the parahippocampal, periaqueductal gray region, sorry, it's along PAG, which is supposed to be a migraine generator. So it all makes sense. And these migraine patients were all without aura. And later on, a couple of years later, we just compared migraineurs with aura and without aura. It seems that they've got all the same kind of headache, but having some visual symptoms just before the headache starts. And it seems that in patients who's got aura, you've got a more extensive alteration of white matter microstructure. And if you are looking at cluster headache patient, you've got yet again a broad alteration of the microstructure. And as a matter of fact, this alteration is even correlating how often they've got headache. And one more structural marker is the thalamus. I mentioned you, that's the main relay region in the brain for sensory information. And if you are looking at migraineurs, compare them with the healthy controls, you can show that the size of the thalamus is increased in migraineurs. And as a matter of fact, the size of the thalamus is correlated with the headache frequency. More often the patient is having a headache, the larger the thalamus is. And if you are looking at which part of the thalamus is affected, is enlarged, you will see yet again fibers going down to the unpronounceable periaqueductal gray matter, which thought to be the migraine generator. So why are these any important? The thing is that running a pharmacological study in any kind of headache disorder is very difficult, because the only marker of the disease currently is that you can ask your patient if you have a headache, right? And that when they are reporting their headache, they are not really good in that. They just keep forgetting they had a headache. They are just try to overinterpret their headache, the length of it, and the severity of it. It's a bad marker. So we need something objective. And that's why we are trying to identify these biomarkers. So these were the structural biomarkers, and let me show you a couple of functional biomarkers. I told you if something is magnetic, will disturb the local magnetic field, will destroy your signal from the brain, right? Interestingly enough, we've got something in our body which is magnetic in some circumstances and non-magnetic in some other circumstances. Well, that's hemoglobin. Hemoglobin is the thing which is transporting oxygen to the body, to the cells. And if an oxygen is connected, hemoglobin is not magnetic. Whenever dissociating from it, is a deoxyhemoglobin. It's a magnetic substance. So you can use it to identify, say, regions in the brain which are activating because neuronal activity will use oxygen, and if it is using oxygen, it will change the concentration of the deoxyhemoglobin, which is the magnetic thing. And usually we are doing that for a minute or so. We are showing some images to the patient or to the subject, which is activating the primary visual cortex, which is here in the occipital lobe. And for half a minute, the patient is not looking anything, just a blank screen. Then you repeat that over and over again. And the only thing you are looking for, those places all over the brain which are showing similar kind of pattern of activity changes or deoxyhemoglobin concentration changes. Well, you can do that in rats. I told you we've got 3 Tesla scanner just installed here in the basement in our hospital. In Budapest, we've got a 9.4 Tesla scanner, which is for small animals. And if you're looking at long-term pain effect, you will identify the anterior cingulate cortex, which is overactivating. I told you anterior cingulate cortex is the one responsible for the emotional aspect of the pain. And the very last point I would like to come is resting state Fmri, which is probably the fanciest thing you can do in imaging today. Our brain, even if you are just lying and not doing anything, is using a lot of energy. Basically, the basal energy use of our brain is 95%. Only 5% what we are using extra for thinking. I keep telling my wife I'm losing weight with thinking. I know it's rubbish, right? And interestingly enough, these activations in the brain are organized into networks. So some of those in that, let's say the upper row, those regions marked with yellow, they're activating together and their activity is fluctuating in time. And that's a very sensitive measure of brain activity. And if we are looking at these networks in cluster headache, we can see that more often the patient is having a headache, more altered this resting activity is. And very same in migraineurs, they've got a higher amplitude of activity in rest. And that could be, yet again, a very interesting biomarker of the disease. And since I had 15 minutes, spot on, I finished with this. Skipping the pathomechanism thing because that would be too scientific, I guess. Just let me show you the guys who are working with my PhD students and postdocs in Szeged on the picture. Actually, we are on the Kékes Mountain last year retreat, and I'm working with guys in the Richtergede on imaging center also, and thanks to them. Thank you for your attention.